Okay, this is the very last example in booklet 2. We have got a context question, so we've got a country, 15% of the people are left-handed. Okay, we're going to have to set up distributional approximations for these things. Well, before I can do that, I need the exact distribution. So look at part A. I want there to be more than 8 left-handed people amongst 70 people. So there are 70 people, each one might or might not be left-handed. I'm counting how many are left-handed. So this looks like a binomial situation at least. Later on we'll actually have to justify any assumptions that are needed. So let's take it that x is indeed a binomial distribution. Okay, so the binomial distribution would have an n of 70 and a p of, okay, the probability of being left-handed is 15%, 0.15. Okay, so n is 70, p equals 0.15. Now I could work out the exact binomial probability of what's it want. It wants more than 8 left-handed people, so that's the probability that x is greater than 8. More than means it's not allowed to equal 8. Okay, but I'm going to set up a normal distribution. So this has all been for the exact distribution. I'm now going to morph this into a normal distribution, and that will include doing a continuity correction. Okay, so for my mu, I need to work out NP. That's the formula for the mean, which is 70 times 0.15, which is going to be 10.5 according to my calculator, and sigma squared is going to be NP 1 minus p, so I need to multiply that by 1 minus p, which is 0.85 if I take that away from 1, so I've got that here, and my calculator tells me that that answer is 8.925. So my approximate distribution is going to be x twiddling a normal. My mean is 10.5, my variance is 8.925, but that's sigma squared. My sigma, which I'm more interested in, is the square root of 8.925, which I can carry on typing it like that. I'm not going to bother getting it as a decimal, but I mustn't forget that square root. Now what I haven't done yet is a continuity correction. For a binomial probability, we'd need to write out 0.789 ... and I still have to, because I need this to get the continuity correction. So I want to be greater than 8, so I'm not allowed to be 0 or 7. I'm not allowed to be 8, because it's strictly greater than 8, so I can be 9 onwards. So my inclusion box would have everything. My exclusion box would have the values up to and including 8. So I can see my cutoff is that my continuity correction is the probability that x is greater than 8.5. Okay, so now I can ignore everything about the original binomial. I've got a normal distribution, I've got an 8.5 value, so I do my sketch. My normal's got a mean of 10.5, so I put that in the middle. The value that I've got from my continuity correction is 8.5, it's this side. I want to be greater than 8.5, so this is the region that's shaded. I'm ready to work out my z, which is the value 8.5 minus the mean 10.5 over the standard deviation, square root of 8.925. I'm expecting a negative value. My calculator tells me the answer is negative, good, minus 0.6695. My sketch says use that as the lower and have an upper of 9999. There we go, press equals, and here's our probability. My answer is 0.7484. Double underline it. Now, just for a laugh, let's actually look at what the exact binomial would have given me. So this diagram would have told me to do 1 minus the probability of x being less than or equal to 8 on my binomial CD mode. Okay, here we go for that. Binomial CD, I'd have said I want an x value of 8, and my n and p values were n was 70 and p was 0.15. And it's giving me this probability here. So if I do take away that value, 1 minus 0.259, okay, then if we do 1 minus that value, then we get 0.741, I think, instead of 0.748. So it is an approximate answer, but it's a pretty good approximation. They're both extremely close to 0.75. Okay, so let's move on. You can check the other answers we get using the exact binomial as well if you want to. It's not a bad reality check in an exam, but obviously don't expect them to be exactly agreeing because it's an approximation. So onwards, part B. Now we've got 200 pupils in the school. We're counting the left-handers. So this is going to be a binomial, same P, but N is now 200. And the probability I want is that it's at least 30 left-handers. So here's all that information. At least 30 means greater than or equal to 30. Remember, for the binomial, that matters. And I'll need that for my diagram. At least 30 means it could be 30, it could be 31, but it can't be these. So my inclusion box would have everything, but my exclusion box comes to there. So my continuity correction's at 29.5. So I'm going to morph that into the probability that x is greater than 29.5 for my normal distribution. Okay, I haven't set up my normal distribution yet, so let's get a mu, let's get a sigma squared, let's get a sigma. So my mu is NP, which is 200 times 0.15, which is 30. My sigma squared equals NP 1 minus P, which is that value of 30 times 1 minus the probability, which is 0.85, which gives me 25.5 for sigma, but I'm much more interested, so for sigma squared, I'm much more interested in sigma, which is the square root of 25.5. Okay, and I know this is a normal distribution, so I'm ready to work out my normal probability. So of course I need a sketch, and the mean of this distribution is now at my mu, which is 30, and my value is 29.5, which is just on this side. Okay. I draw it so it's convenient for me, and I want to be greater than that value, so we shade these in. So my z value I'm going to get as 29.5 minus the mean over the standard deviation, which has got a square root on it, and I get a z value of, here we go, it's a negative z value, but it's not very big, which is what I'd expect because it's below the mean but not by very far. So there's my z. I can see that I need to be using that as my lower, and that my upper is going to be 9999. So lower is minus 0.099. Okay, upper is 9999, that's right. So my probability is 0.539. Now at this point, we've done A and B. Part C you can do for yourself. Just be careful that you correct the question. If you've used the version off the video, it's wrongly printed, but in your booklet it will be correct. So the correct version of the question has a village of 2,200 people and between more than 300, but fewer than 320 being left-handed. Okay, go ahead and do this. Then fast forward the video and check you've got the right answer. Go on, do your own work before you look at this. Pause the video. Okay, if you're unpaused, then you should have looked at this set of outcomes, and we can't be 300 or 320, so therefore my inclusion box comes here, and my other box like that, so that my cutoff values are actually 300.5 and 319.5. I need to set up a normal distribution with a mu and a sigma. So using NP, my mean is 330, and before getting sigma, of course, I'm going to get sigma squared using NP 1 minus P, 280.5, but of course what I'm really interested in is sigma, which is the square root of 280.5. So this is my normal distribution, my approximately normal distribution. Okay, and I've got the probability from that distribution, so now all I need is the diagram. I need to lie between 300.5 and 319.5, so here they are. So each one's going to have a z value. I'm going to get a z1 and a z2. There's z1, and it equals minus 1.761. And for z2, we get minus 0.627. And using those as my lower and upper, I get my probability of all the 2's. Double underline it, and that's my answer to part C. This being the correct part C, not the way this was originally printed. Hopefully this is right in your booklet. Okay, won't be long to finish this now. What assumption have we made in each case when setting up the exact distribution? Okay, and how realistic do I think that is? So we've got to be careful here. There's a hint here. Part E is asking the justification for the approximation. So it's not at this point that I start looking at NP and NP1 minus P. It's the assumption for the binomial. So what assumptions do I need for a binomial? Well, I need a fixed probability of success, and I need all of the trials to be independent. Now, if you look at the question, okay, remember the P of 0.15 comes from this, which is fixed. So that's not an assumption that P is fixed. However, in each case, the idea about independence will be an assumption. So I can lump all of these together and say that in each case I've assumed that people's left-handedness will be independent, if I say that better. Okay, so assume individuals in each group have an independent chance of being left-handed. Okay, now is that going to be realistic for all the groups? So I had a bus, I had a school, I had a village. So why would one person in any of those groups being left-handed change the chance of someone else being left-handed? Well, I suppose there is a slight inherited factor of left-handedness. You're slightly more likely to have left-handed children. So possibly if there are family groups involved, there might be some non-independence going on. Can't think of any other obvious reasons. So it's not an unreasonable assumption. So I can say it's a fairly reasonable assumption, though in the school and in the village there may be families where there's a bit of left-handedness running in the family. It's not a strong effect, but it can happen. So that was part D about the assumption necessary to set up the exact distribution, the binomial in the first place. It's part E where it's asking us to justify the approximation. So that's where we talk about NP and NQ. Now in the first case I had n equals 70, P is 0.15 of course. So NP equals, NP is 10.5 because I worked that out before as the mean, and n times 1 minus p, not np1 minus p, n times 1 minus p is 70 times 0.85, which is going to equal 59.5. This is greater than 10, this is greater than 10, so our comment is both np and n1 minus p, n1 minus p are greater than 10. Okay, and I'm going to do precisely similar things with the others. I mean, I can tell they're going to work because n is getting bigger and p staying the same. So for the school you got 30 and 170, for the village it's 330 and 1870. So the same comments are made, both np and n1 minus p are greater than 10. And in an exam you'd write this out properly. They're asking us to do the same thing, so effectively 3 times. I've been a bit lazy, but hopefully you've got the hang of that. Of course, we have to finish by drawing our conclusion. Therefore, so we need 3 things. We need the values, we need the statement those values are greater than 10, and then we need at the end the claim that the normal approximation is appropriate, which we've backed up with our numbers.